In this video, we're going to review partial integration. So what do we mean when we say partial integration? So this is the integration counterpart of something that we already know, which is a partial derivative. The big idea here is that we want to, or let's say we have a multivariable function. So for example, a function that depends on, let's say, both x, y, and z, and you want to integrate that function, but only integrate it with respect to one of those variables. So with respect to only one variable. So this is, of course, in contrast to normal integration or ordinary integration, where, for example, if we have a function that depends solely on one variable, so f of x is a function of x, so we'll say f of x is equal to x squared, then we can integrate f of x dx, and we'd find that this is equal to x cubed over 3 plus some constant c. But in partial integration, we deal with functions that are variables, or functions that depend on multiple variables. So let's say instead that our function here depends on x, y, and z. But the function is x squared that we want to do the partial integration on. So in this case, we're integrating f of x, y, and z. We're doing that with respect to x. So I use the partial del x here. And in this case, we're going to have x cubed over 3 plus some unknown function, which we'll call g, which is a function of y and z. Now, why do we write this as g of y and z? What values could g of y and z take on? To illustrate that, let's pick some values for g. So let's say that g of y and z is equal to y squared plus z squared plus some constant c. So now we have our function f of x, y, and z, and we can take the partial derivative of that of f of x, y, and z with respect to x. So when we do this, we have del by del x of our expression, which is x cubed over 3, plus g of y and z, where g of y and z is y squared plus z squared plus some constant c. So when we take the partial derivative of this with respect to x, we end up with 3x squared over 3. The 3's cancel out, and we're just left with x squared. And we can see that this matches our original function, f of x. Now what this means is that g of y and z basically goes away, and because of that, we have infinitely many valid antiderivatives. So for example, this function here, this could have been anything else. So it could have been y cubed plus 10z squared plus c. It could have been y to the 4th plus yz to the 3rd plus c. There are infinitely many valid expressions that could have been, as long as it doesn't depend on x. And so that's why when we take the partial derivative, we have to include this g of y and z term just to account for whatever that function may be.